Hello everyone, I am Angela and I'll be here as your tech support during this tutorial. I would like to introduce you to our tutor, Mihael Jaksic. He is a teaching and research assistant at Faculty of Electrical Engineering and Computing at University of Zagreb, and he will be holding the identification of building thermal model using data tutorial today. I hope you enjoy it.
Okay, hi, hello. Welcome to my presentation and thanks, Angela, for introduction. Welcome to you all. I'm so happy to be here for the second time to present at the Data Science Conference for the second time. First, I will share the screen with you. So please tell me when you can see it in a moment. Can you see it?
Yes.
Okay, so well, last time we were talking about photovoltaic cells production of the electricity. This time something maybe a bit similar, but also completely different. This time we're talking about identification of building thermal model, but using data. Identification of building thermal model is just a fancy way of saying we're actually predicting the temperature in the building zones. I will explain it in great detail, and I have to warn you, this might be a bit more theoretical lecture than you are used to, or maybe you would like it to be, because I need to explain why do we do what we do, why do we need these predictions, and what are we going to do with it. And we also have our own experimental setup where we got the data, so I have to explain that. So let's dig into it. So first of all, as Angela already said, I'm coming from Faculty of Electrical Engineering and Computing, University of Zagreb in Croatia. The faculty counts around 3,500 students. We have 500 Masters of Science annually and around 700 employees. Currently, the faculty holds 260 projects worth approximately 400 million euros. And actually, from these projects, we pull about 50% of the faculty financing. We also have a Center for AI and other experimental centers. Okay, just give me a moment, sorry. Okay, I'm coming from laboratory for renewable energy systems, where we have approximately 40 people employed, and more than 10 of these people have PhD. Currently, we're having 20 ongoing projects. Some of them fundings come from Horizon Europe, IRI2, STRIP, Interreg, Croatian Science Foundation, and others. Approximately all the projects currently held at LARES laboratory are worth approximately 10 million euros. 85 of employees in the laboratory are researchers. What do? We do AI in sustainability. We use neural networks and machine learning algorithms. We're actually forecasting disturbances and uncertainties stochastically, using some meta-heuristic approaches and several others, and applied to renewable energy systems, smart grid, smart buildings, city infrastructures, and agriculture. Okay, so first question we have to start is, why do we want building model identification? I'm going to dive deeply into it in the next slides, but let's just get a brief overview. So we want to create the future, a model of future system behavior, and we want to control the system using this predicted behavior. What do we do, or actually what do we need to do that? We need time series data. We actually captured at one floor of fair skyscraper. We also need weather forecast and a little bit of coding and AI magic. So let's start with theoretical introduction. As I said, and once again, I'm going to say it, this is going to be a bit more theoretical presentation than you would normally expect, because I have to explain our experimental setup. I need to explain why do we need this and what is our goal. So buildings consume approximately 30% of global primary energy demand. And the goal of the European Union, United States, and several other countries is to reduce this energy consumption. You can actually go two directions with it. First, you can construct the new buildings using better heat insulation, which is fine for the newly built buildings. However, most of the buildings are of the older date, and they are in need of refurbishment with new heater insulation, which actually needs significant financial investments. However, if you dig deeply into the data, 60% of this 30% in building energy goes towards maintaining thermal comfort. So one part of the solution is to retrofit the older buildings with the new building management systems, or BMS, and apply some sort of predictive control algorithm to it. The idea is to optimize the thermal input while maintaining the thermal comfort. Basically, you're using less energy while the user would not probably see the difference. For example, every morning I come at fair at skyscraper. Heating at fair skyscraper starts every morning at 6 a.m. and I come to my office at 7 a.m. And the first thing I do when I come to work is open the window. And then I make coffee, of course, just as any other data scientist would. What is the problem here? Well, the problem is that thermal energy input between this 6 a.m. and 7 p.m., 1 full hour of thermal energy input in the room or zone goes out. And that is wasted thermal energy, which means wasted money. The solution is actually to use control algorithm for optimization of the thermal input for all the zones, or basically to find in future the algorithm that would predict my behavior, that the moment I come to work, I open the window, and then use it as a part of control algorithm for thermal input. Basically, that algorithm would probably not turn on the heating or cooling before I close the window. And that would save 1 hour of energy, and that is just for my part, just for my office. And we have 246 offices in that building. Okay, there's another problem. The another problem is modeling thermal comfort, because it accounts for approximately 70% of engineering cost. Traditionally, you would model the whole building using professional building thermal behavior simulation software. And you have to be very, very, very precise with materials if you want a good simulation. Our colleague Anita from our laboratory has done it in great detail, and she has spent more than 1 full year trying to model the building in professional simulation software. As I said, it requires a lot of work. Plus, you need it. It's not ideal for real-time control, which we almost need. Not maybe real-time, but once a day would be nice. Then, when you have the simulation result, you have to run the simulation results through Unscented Kalman Filter to obtain semi-physical model parameters, which actually needs dabbling with a lot, and I mean a lot, of complex mathematics. And then the third step, when you've done all of that, is to create and run semi-physical model with discovered parameters. Again, there's a lot of complex mathematics behind it, and it's actually time-consuming. How are we going to approach it here? Or actually, how did I approach it here? Well, using data. We have installed during one night our equipment to 25 zones on a single floor of fair skyscraper. Normally, you would need expensive building management system, but our approach is to use regular smart home devices and controllers that use Z-Wave wireless protocol, opposed to more traditionally used ZigBee. In our case, Z-Wave has proved to be more resilient to breaks, and its frequency is more closer to Wi-Fi signal, and therefore it breaks less often than traditional ZigBee for smart home devices. These are actually smart home devices. You don't have to be an expert to install. You can buy them in almost every electronic convenience store you can find in your city, almost any. So here's our 9th floor at Faculty of Electrical Engineering and Computing skyscraper. So these pink circles are the motion sensors, or quad model-light sensors, which capture motion if the window is open, temperature, if anyone is in the room, and lightning. Then we have air quality sensors, which capture CO2, value organic compound, and temperature, and I can't remember 2 more variables which we are not going to use. And then we have 25, as much as there are zones, as I said, 25. There are 25 controllers. One is on the, actually 12 are where the left blue star is, and 13 are where the right blue star is. These are smart home controllers. Why do we need 25 of them? Because our idea is to run our optimization algorithms independently. Or actually, we want each zone or each room, zone is just a fancy term for room, to have its own controller. And that is it for 9th floor. How does it look? What did we do? Actually, we have a lot of sensors, like at least 2 per room, maybe even 6, up to 6. They control via wireless Z-Wave protocol to smart home device or smart home controller. Then it sends the data to cloud server, from where we pull the data through regular TCP/IP and RESTful API to our data collection server. Then we can use these predictive algorithms and optimization algorithms to control heating and cooling in the building by sending a signal also through REST API to smart home controller, and then he would direct it to a relay or actuator more generally, and he would control heating and cooling device in that zone. Okay, let's just explain experimental setup a bit more in detail. Each room has distinct smart home controller. There are 25 in total. We have one air quality multi-sensing device, and we have at least 1 and up to 5 quad multi-sensors. Sampling time is 15 minutes, or actually every 15 minutes we send a REST request to get the new data to get the new data from cloud server producer has provided us. And then we've got an insider info. As they say, vending machines CPUs spend approximately 90% of the time in idle, which is similar to our controllers, because every 15 minutes we would ask for the data, not more often than 15 minutes. So our idea is to run optimization algorithms on our smart home controllers. And here we come to a new trend of AI, in AI. It is TinyML or Tiny AI. It actually it has several benefits. For example, first is low electricity consumption. You don't need complex PCs, complex servers, or anything. You can actually run it almost on your mobile phone. Secondly, it uses as little data as possible. Then you don't need huge data sets, because you can use, in our example, 1 week of training data, which will be just enough. And also, with little amount of data and with lower complexity algorithms, models can be quickly retrained, which are all the great things we need for our smart home controllers. So let me propose the experiment I did and we're going to go through. So first, we take 1 week of training data as training data, and then we test on the next 24 hours of data. Then we move the sliding window. We discard first 24 hours of data and take the previous test set as a new part of our training set. And then we test on the next 24 hours of data and so forth, and etc. The thing about this experiment here for this tutorial is that it's limited just on one zone. I'll explain why I'm saying that a bit later on. So let's dig into the data first before we continue. Okay, here I've prepared some sort of Jupyter notebook. It's actually a more modern version of Jupyter notebook. So can anyone please confirm, can you see it? And if the font size is okay to you? Anyone?
Yes, we can see it.
Okay, is the font size okay? Shall I enlarge it?
I think it's okay.
Okay, thank you. So yeah, you'll probably get this presentation after I finish with this tutorial. So here are some contact info in case you have any additional questions after the lecture or in the next few days, or actually you can catch me up in the next few days at the Data Science Conference. So first, we start with importing basic libraries or Python modules. We're going to use pandas for our dabbling with data. We're going to need to plot this data, for which we're going to use matplotlib or pyplot. We're going to use NumPy, tqdm, which is actually just a nice way to have loading bar in our Jupyter notebook or Jupyter lab, if you like. Okay, operating systems then, inbuilt Python library, random, also inbuilt Python library. Then we're going to need the info on date and time, sorry. We're going to calculate mean squared error. We're going to need to select the model, for which we're going to use time series split, which I'm going to cover a bit in a bit more detail later on, and also grid search cross validation. Nothing actually gets without it. Then we're also going to use, okay, and now I realize I've imported mean squared error twice. Well, it doesn't make any difference, but okay. And also mean absolute error. We're going to need some mean, light GBM as the model that has proved itself to be the best on this data set. We've actually tried several of the models. I'm going to explain it a bit later on, as I said, and TQDM, well, once again, why not import it twice? Also, we're going to filter out warnings for this presentation because, as you already know, none of the warnings and multiple warnings, they're the same thing probably. Okay, let's start with data loading. So we have two parts of the data set we'd like to combine. One is the outside temperature. Okay, it's not outside temperature, it's actually prediction of the outside temperature since it influences on the room temperature. The thing is, the higher the outside temperature, if the heating or cooling is off, then you'd expect the room to be warmer or cooler depending on the outside temperature. So that's why we use the weather forecast. The second data set is actually the data from the zone we have actually pulled from our database. I didn't pull all the data or all the features. I just pulled the ones we might need and some others to show you what do we have. Some of the features that we have in this data frame, for example, is weekend, is vacation, and working hours, are already pre-engineered from timestamp, and since they played an important role in the zone temperature, because if the date is vacation, then you would not expect air conditioning or heating to be on. Actually, if it's outside working hours, you would also expect heating or cooling to be off, and during the weekend too. Maybe some people come during the weekend because the building is open 24/7, and then they would turn on the heating or cooling manually, which is completely fine. But we need this data just to give our model a rough overview of how it's going to behave. Okay, so first we load our first data set, which is temperature air, or as I said, prediction or weather forecast, temperature forecast for the outside. Index column is 0 or this timestamp. Then we actually set the column name, which I don't have in my data set. I have to do it manually here. I'm going to put the index name as timestamp. I'm going to parse index as date time, and then I'm going just to show you ahead, and here it is. For example, our experiment, or actually the first time we started to collect data, was 28th of July in 2022 at 4:50 p.m. The air temperature was 40, or actually predicted air temperature was 40. 15 minutes later, sorry, I completely forgot about that. Our sampling time is 15 minutes. Every 15 minutes, we send a request. And any data between those is actually discarded completely. Okay, then we have the data for our zone. As I said, this is not complete or comprehensive data. This is just part of the data. And due to privacy reasons, currently, we're not saying the zone ID, this is just some zone. Once again, the index is going to be timestamp. We're going to do it in place. Index, we're also going to parse this timestamp as timestamp, and we're going just to show head of this data frame. As I said, we have CO2 measurements. Z comes from zrak, which in Croatian or most of the Balkan languages means air. So it's coming from air quality sensors. Also humidity. Motion comes from quad sensor at the window. Also, this is room temperature at air quality sensor, room temperature at quad multi-sensor at the window. As you can see, it's during summer, and window actually got some heat, and while the room air did not. This is the difference we're having. Also, if the window is open, is the weekend, is the vacation currently, is it inside working hours? And here we have additional feature, which is average temperature. I'm going to explain it a bit later. Yeah, I think so. Yeah, okay. Then we're going to merge out this outside temperature data frame with zone temperature data frame. So currently air temperature comes here to our left, and that is all you need to know. Everything else is completely same. Okay, the features are currently as follows. So we have air temperature. as I said, it's outside air temperature prediction in degrees Celsius, CO2, amount of carbon dioxide in ppm or parts per million, humidity, motion, room temperature by air quality sensor, room temperature measured by quad multi-sensor mounted on the window. Then window, which is binary variable, if the window is open, is weekend, is vacation, and working hour. Hours, all three of these are binary variables, which are more or less self-explanatory. And then we have average temperature, which is average of measured zone temperatures. Because when you're dealing with multiple sensors that measure the same value, in some zones we have up to 6 temperature sensors. Yeah, up to 6. Then averaging their values is a common approach, and it has 2 advantages. First is that we never know what the ground truth is, but by averaging values, we consider we're closer to the ground truth. And secondly, if the sensor is broken or gives values that are significantly off the average, then it's easy to spot which sensor went broken and discard its values. Okay, now we probably know, we've just dig into the data, we know what the features are. Let's start with some plotting. Of course, this is not all the plotting I did. This is just shorter version of plotting for the sake of this tutorial, because we don't have too much time to go deeply into it. So first we'll start with outside air temperature. It oscillates, of course, every single day at night. However, well, almost like a sine wave or something, or maybe cosine even, with a lot of noise. You would probably describe it. But here is how it looks for our data set, for our data collection period. We have started data set on 28th of July in 2022 and stopped collecting data on 21st of July this year. Okay, we have the outside temperature plot. Then we actually have 2 plots, or actually 3 things plotted at the same graph. This might look noisy. We have this temperature average we're trying to predict later, and a bit bigger so you can see it completely. Here, basically, we're plotting the temperature measured by air quality sensor, then we're plotting temperature measured by quad multi-sensor on the window, and then we're plotting the temperature average. This graph here, as it's displayed, is not very informational. That's why we want to continue with different graph, which shows it a bit larger. So here we're going to get the data, but only for first full week of data, for data recorded. So first, blue one is the data from air quality sensors, or temperature measured by air quality sensors in our zone. Then the orange one is measured by quad multi-sensor. Here, because it's wireless, we're having a bit more connection losses than normally you would via wire, but that's the difference. Like, you can get these sensors at around 100 euros, even less, sorry, 50 euros a piece. And professional building management systems, it comes like much, much more. And then we calculated the average temperature for these 2 sensors, and we're considering that to be the ground truth. Sometimes the sensors are off, but that's okay. The temperature average will probably take care of it. Okay, here on this plot, we're just having average temperature for this zone for first full week of the data. And then we come to feature engineering. Well, all the models work better with more features, and we've tried to introduce a few. The thing is, also, although in our data frame, you have all these features, we've had to discard some of them because we can't predict CO2, we can't predict humidity, we can't predict motion. We're trying here to predict room temperature, which is okay. We can't predict if the window is going to be open or not. We can't predict that for now. For window, maybe if we find some patterns in the data, but for CO2 and humidity, it would be a tough job. And we would have to see some heat maps, correlations, and so on. Since we can't predict that, or if we wanted to, we would need to have room temperature. So that's actually a vicious cycle where you want to predict first thing, and then you need to predict second thing, and then you need to predict first thing, and so on. Basically, you're in a vicious cycle. That's why we decided to discard all these 2 also, because these 2 are actually contained in average temperature, and also we decided to discard window openness. So what we are using is some sort of calendar. Basically, we're trying to check the trend and how well are algorithms or models able to adapt to the trend. So first, we'll have the date, then the air temperature, then hour, which we're just going to pull out of the index, then day of the week, quarter, because heating or cooling depends on the quarter. Maybe you'd want to heat in winter, but also maybe in late autumn, maybe in early spring, and you'd want to cool in late spring, early autumn, and during the summer. Also, month data, year, a day of the year, day of month, and week of the year. Okay, here they are one next to each other. Okay, also we're keeping is weekend, is action, and is vacation, and working hours, as I've already explained. We're also going to introduce some lag features because we want to give the algorithm as much data as we can, and we're actually going to give it 6 hours before of data, so that it's hoping it can generalize well enough to capture the trend. So here, although it seems we're making 24 hours, no, we're not. We're actually making 24 measurements, which are adapted to 6 hours. As I said, 6 hours, we have 4 measurements per hour, which is exactly 24 steps of lag. And we're using this function I've already went through to create these lagging steps. After that, we have, of course, we're returning X as learning features or learning set, and Y as the output set we want, as the set we want to predict, basically. Okay, now here we're having head or first 5 rows of this X learning data set. As I said, all the data is similar, or as I've explained it already, but we're having here some nans. Why do they occur? This is the thing that actually baffled me the first time I saw it, but there's a pretty simple reason for that. Because if this is the moment 0, when you first started capturing the data, then there's no measurement 15 steps before it. There are measurements 15 steps after it, maybe. There will be, but 15 steps before it, no. That's why the nans are here, and we will discard them in a few moments. Here you can see all the columns in the X or our data frame, and we're starting with first Monday because it's completely natural to us to start with the first Monday. This actually, I did an article or paper with a different topic, and we've had 24 hours of lagging features, not just 6 hours. And that's why we wanted to start on Monday, first day, where we have full data and lagging features too. Also, the last full day of the data was 21st of July this year, 2023, as I've already mentioned. And basically, this is going to be our last day for testing. This will be last day for testing. We have some data from 22nd of July, but it's not full day, and we want to test it on the full day, because maybe we would want to retrain our models during the night for the following day. Okay, once again, okay, we already showed that. Tail, I usually like to display the tail of the data frame just to show where do we start, what is happening here, and here we're having, as I've said, lagging features. Okay, also what we want to predict here is Y, or output variable. The timestamp is the index, and here are temperature values or average temperature for the zones in degrees Celsius. First 5 rows, last 5 rows, and we can see the data type is float 64, which is fine. Okay, as I said, we've tried for this several AI or machine learning models, not several, but 6. We've tried to experiment with the longer learning time, with bigger data sets, but this has actually proved to work quite fine. And I'm going to dabble into it a bit more in a bit more detail later. So let's start with experiment and our light GBM model according to already proposed experiment. As I said, we're taking just 1 full week of data as our training set. And then we're testing on the following 24 hours of data as our testing set. And then we will move this window until the end of our whole data set. So our X-train had, once more, I usually, when I'm dabbling with some sort of data, I usually like to print it out, just display myself the first 5 rows. You will see these all in all my notebooks, Jupyter notebooks, probably, because I just like to see what is going on, what's happened, how it is going, how is it happening, what am I changing. Okay, so this is X train, and it ends on 7th. Maybe I can add just okay. Then I would have to do this, and maybe I can show you the tail, so I'm not cheating. Okay, the test ends on 7th of August 2022 at 11:50 p.m. Then we're having X test and its head, and this is just 15 minutes. Sorry, this is the data 15 minutes after this training set, or actual last entry of the training set. And here we're having the same data, also some lagging features. We're having lagging features here, you would see them, but we're actually replacing these lagging features with the predicted ones so that we're not cheating here. And then we're going to, I'm going to explain it in a bit more detail later on as I'm going through the notebook. Then we're going to use time series split as part of our grid search strategy. Time series split is actually a library from scikit-learn. You can find it, and it works a bit differently than any ordinary grid search cross-validation split, because here it takes the first training set, actually splits the data into several parts. Here it splits the data into 4 distinct parts, and then takes the first part as training set and second part as training set. Then it retrains on the first and second set or part and tests on the third set. Then it takes this third set also as the training set and tests on the fourth part of fourth set. And then it takes all 4 parts it has tested before and then tests on fifth set. This is how it works, and this is also similar to our idea, to the idea of our experiment here. That's why I put it here. You can find it actually in the official time series split documentation. Maybe I should have put literature or something, literature overview here. I will put it and upload it, this Jupyter notebook to you. So we're using time series split. As I say here, we're using 4 splits because we don't have that much data to split it into 5 or even more than 5 parts. We're using LightGBM regressor, verbosity -1. Here, for the sake of this Jupyter notebook, it is -1. Normally, I want it not too verbose, but more verbose so that I can see what is doing. But here, I've just put it on -1 because I don't want any distractions. Also, you can put the number of jobs you want, and I put it to CPU count divided by 2, so it doesn't take all of my CPU here. So here are the parameters it is searching through, and then we're starting our grid search with our estimator being our LightGBM regressor, using CV split here, time series split, and param grid here as our parameters we've defined here. I did not run this for you because I didn't have time. I'm sorry. I'm not going to run it here too. I'm sorry too, because you will be able to run it later and we would take too much time. It would take approximately half an hour or something to find optimal parameters for this model with these parameters provided here. So basically, you're going to have to believe me that I've found that using this and this, I've found the optimal parameters for our data set to be these here. And then I've defined my LightGBM regressor with these parameters, or the best parameters here. And I actually fit it with X train and Y train learning sets. Okay. Now we come to a different function, maybe something you didn't already see, which is completely fine. As I said, we can't cheat with data. It's not fine to cheat with the data. It's not okay. That's why we're actually using the predictions, our prediction, as a part of X test set. Basically, we want to shift data frame values so that the last predicted value is the first lagging feature of the next moment. That is exactly what we're doing in this function here. First, we'll start with test shape because we're having 24 hours of testing data, which is 96 examples with 15-minute sampling time. Basically, we sample 4 times an hour, 24 hours times 4 comes to around 96, not around, but exactly 96. Okay, so what do we do here? First, we define an array for our predictions, and then for every single row in X test, we will do our prediction, but we will take only the first value of this prediction. Not sorry, the first, but the corresponding to the row we're actually predicting on. Why? Because we're also going to use this prediction for our shifting value. Because, as I said once more, I want to make it clear. Okay, we're having lagging features here. And then we can't use the lagging features 24 hours in advance because we don't have the information on 24. We have, but we can't cheat with the data. We have to replace them with our predictions. And then we can use it completely okay. Then it would be okay, because then we rely only on our predictions. But any other way, we would lie with the data and get the models that are cheating, that are lying to us, and also are not working very good in production. Okay, as I said, we have X test, and every single iteration that is greater than 1, we're going to shift these data frame values, and to the corresponding row, we're going to add our prediction here. Basically, to the corresponding row, as I said, temperature lag for first step is this predicted value here, but for all the others, we're just moving one step to the one place to the right of the previous step or the previous row. Okay, and after running all of this, we have these predictions. And then we can actually calculate mean absolute percentage error here, or some other matrices here, like mean squared error, or mean absolute error, or mean absolute percentage error. We're actually calculating all 3 of these because one would not probably give us good enough information on how well it's behaving. Because when dabbling with Saramax, we've had mean absolute error to be approximately 0.5, and mean squared error, we've had it to be at around 10 or something, I can't remember correctly. So it's found some mistake, it's found some problem, and then squaring does it, skyrockets it, basically. And here it is, the mean squared error for this data set is 0.1466. Mean absolute error is 0.3, let's say, which means basically we're overshooting and undershooting on average 0.3 degrees Celsius, which is completely fine for our model. And mean absolute percentage error, well, 1.2%, let's say we're missing by 1.2%. And then we would want to plot the results, and here they are. Basically, the blue is the data we have really measured in our experimentals, and the orange one is the predicted values, using, of course, the trend but prediction trend. Okay. Then, when we found the correct parameters, when we have tested this, when we have showed that it works completely fine for just first full week of the data, then maybe we would want to run it for all the data we have for a single room. So we have to count the total days we're having, And we also declared some arrays for mean squared error, mean absolute percentage error. And then we are going to, for every single day, we're going to pull the X train and Y train as the 7 days data set. Of course, we're going to use copy. We don't want to change the original set. We're also going to use the following 24 hours as our test set. And as I said, we're moving this horizon through our whole data set. And here you're going to see something different. Here, we're not trying to do the grid search because we don't want to do it every single time. It's complex, and it will take a lot of time and a lot of computing power for every single week of the data, especially using it on our smart home devices or smart home controllers, if you like. It's going to kill the controllers basically, and they won't be able to communicate with the sensors when we need it. So basically, we're supposing that the system will behave identically in the future. That's why we're using already the same parameters we have discovered here during our grid search and time series split. We're using completely same parameters. These are the parameters we've actually got there. Okay, and then we're doing completely the same thing. For every these two pairs, we're fitting the model, and then we're predicting next 24 hours. How? I've already explained how. I've already explained these stepping predictions and how do we use them and why we can't cheat with the data. And for every single of the testing sets, for every 24 hours of the testing sets, we are appending mean squared error, mean absolute error, and mean absolute percentage error to their respective arrays or lists. And here they are. So minimum, mean absolute error, mean squared error, and mean absolute percentage error are as follows. Minimum mean absolute error are 0.2. Minimum mean squared error are 0.077. Mean absolute percentage minimum less than 1%. Of course, sometimes it's going to behave completely differently, which is also okay. And the maximum overshooting or undershooting in absolute values terms is approximately 1 degree Celsius, let's say, mean squared error 1.516 or 7, and the maximum percentage error is approximately 4.2%. And then mean for the whole data set, for the whole experiment, is somewhere around 0.335 for mean absolute error, 0.225 for mean squared error, and 1.66 for mean absolute percentage error. And here we're actually getting the maximum mean absolute percentage error, and we'd like to plot it to see where our model overshoots or undershoots. And you can see that our model, okay, let me zoom out, maybe you'll see it better now for this graph. Okay, well, it's almost the same. The graph size is also, okay, it's completely the same. But okay, so the measured data has gone down and the predicted is up. That's the main problem. And when you take a closer look of the date, it's actually, the date is still during the vacation period. And that's the main reason why there's significant overshooting, because the week before this date was still a vacation. This is still during vacation, sorry, but nobody was in the room. The person did not use air conditioning. And then when the day comes, this 22nd of August, the person came to the room and then turned on the air conditioning, as you can see. And then our algorithm didn't know what to do with it because the air conditioning was not turned on last week. Also, we would like to see how well it behaved on the data on actually the week, or actually, testing set with the lowest mean absolute percentage error. And you can see it here. It's not perfect. It's actually some discrepancies. Sometimes it undershoots, sometimes it overshoots, but it's completely fine. We're already in 0.2 degrees Celsius area, which is completely fine to us. We can use it for our experiments. Okay, And this is basically the end of our building modeling Jupyter notebook. So let me continue back to our presentation. What can we conclude from this? Well, basically, we can conclude that TinyML is the new and exciting AI development direction. For this example, it works almost as good as the full-size model tested on 340 plus days of data. Unfortunately, I couldn't prove it to you now because I am presenting this data or this solution at 31st Telecommunications Forum in 2 days. And that's why I can't give you the same thing I'm presenting there. It's a strict rule for scientific conferences. This TinyML and this approach is lightweight and it allows models to be retrained a few times a day. And it's a bonus. You can basically run smart home controllers. The training period will probably be somewhere around 1 minute or less than 1 minute. So we can actually retrain a few times a day, maybe even. As I said, more on this topic, if you're interested, you're very welcome to this Wednesday at 31st Telecommunications Forum, where I will be giving presentation for my paper, Data-Driven Model Identification of Building Thermodynamics. There, we're comparing 6 algorithms. Some of them, actually 3 based algorithms, are tested with much larger training sets. And the full paper will also be available through IEEE Explore very soon after the conference. Okay, finally, I have to give some acknowledgement. This work has been supported in part by Croatian Science Foundation under the project grant for Project DECIDE Distributed Control for Dynamic Energy Management of Complex Systems in Smart Cities. And that is it from me. I'd like to thank you for your attention. I hope this was insightful to you. I hope you've learned something new. And if you have any additional questions, please let me know.
Well, if there aren't any questions, I would like to thank you, Mihael. This was very interesting and informative. And thank you to everyone who tuned in and watched the presentation as well. All right, I guess that's it. Thank you, and I'll see you at the conference. Goodbye.
Okay, thank you everyone once again for listening to this presentation. If you have any additional questions, please catch me up at the conferences. I'm sucker for coffees, and you're very welcome to coffee. So, thank you and goodbye.
Bye.